All right, we're going to start on chapter 10, or chapter 9 and then 10. Very similar chapters. We're going to be doing Lewis structures. All right, so chapter 9 is ionic and covalent bonding. Remember, ionic, metal, nonmetal, covalent, two nonmetals. Ionic is a transfer of electrons. Covalent is going to share electrons. All right, so a chemical bond is just a strong attraction force that exists between certain atoms in a substance. So we're going to have three types. Ionic, remember this is a metal with a nonmetal. And this is going to be a transfer of electrons. All right, so simplest is sodium and chlorine make sodium chloride. All right, so to balance that, you have this. All right, so now you have sodium, which is here solid metal. So its oxidation is 0, and all sodiums in compounds are +1. All right, so you oxidize your sodium, your chlorine, oxidation element on the periodic table, 0. In sodium chloride, it is a -1, so that was reduced. All right, so this is a oxidation reduction reaction, but the key is here you have a metal and a nonmetal, and we write a +1 and a -1 because your electron configuration of your sodium is neon 3s1, and then your chlorine is your neon 3s1, then a 3p5. All right, and so this electron that's alone in this s orbital transfers up into this 3p orbital, where now the 3p has a full valence shell. All right, so it's a 3p2. All right, so you have your 3s2, and then your 5 electrons in your 3p. All right, so now when this electron gets transferred, now you have the electron configuration of neon here. That's why Na is going to be plus. The electron configuration of Na plus is simply a neon core. The electron configuration of Cl minus is simply an argon core. All right, and so that is why the electron is going to be transferred. When you're looking at covalent bonds, now you have a nonmetal with a nonmetal, and they share electrons. And then metallic bonds we will do later. We're going to focus on ionic and covalent bonding. All right, so here is ionic. All right, electrostatic attraction between a plus and a minus, the Na plus, Cl minus. All right, so here's the example that I just showed where your 3s1 electron is going into the 3p5 to make it a 3p6. Now this is the electron configuration of argon, and this of course is the electron configuration of neon. All right, you need to know terminology. You got to know if you're a plus charge, you're called a cation. All right, if you're a negative charge, you're called an anion. All right, and so you would say a sodium ion, and that is fine. Sodium is always +1. A better name would be a sodium cation, is therefore Na+. All right, instead of saying the chloride ion, you would say the chloride anion. All right, so the chloride anion. All right, and that's Cl-. But if somebody says they have the chloride ion, we know that that is a negative, but it is important to know the terminology: cation, plus charge; anion, negative charge. All right, so now we're going to do a Lewis dot symbol. So now we're not going to write out the entire electron configuration for sodium. We are going to say that sodium, we just did it, is neon 3s1. And so we're going to put one dot on the sodium. That is the one valence electron that the sodium has. And then we're going to draw the Cl Lewis dot structure. We know that that is neon, then 3s2, 3p5. So there's 7 dots to write on the sodium. And so we write 7 dots on the sodium. All right, and so this is a metal, and this is a nonmetal. And so they're not going to share electrons, they're going to transfer electrons. So this electron is going to go to this Cl. And we're going to end up with sodium without an electron, which makes it positive, and a chlorine with an extra electron. Now it has 8, and that is a anion. All right, and so your Lewis dot structures. All right, so if you're in column 1, so everything in the same column with sodium all has 1 dot. The +1 column, why is it +1? Because it wants to lose 1 electron. And so every Lewis dot structure in column 1 has 1 dot. Column 2 is all +2 because they have the noble gas and then a S2. They want to lose both of those. And so if we're writing magnesium, for example, it's in the +2 column. That means it has 2 electrons. And where you put these 2 electrons does not matter. All right, so then we skip through the D's, and then we go to the column that has boron and aluminum. So if we have aluminum, that is in the +3 column. It has 3 dots to put on the aluminum. All right, so then we have carbon. And so carbon will have 4 dots. If you go across the periodic table, you just keep adding a dot. Everything in the carbon column will have 4 dots. Again, doesn't matter where you put the dots. Then you have nitrogen. That's going to have 5 dots. Again, I don't care where you put the 5 dots, but nitrogen will have 5 dots. And everything in the nitrogen column will have 5 dots. Oxygen is going to have 6 dots. Again, I don't care how you put the 6 dots around the oxygen, but it will have 6 dots. These dots are electrons. They're the valence electrons. All right, and so then if you have fluorine, that has 7 dots. All right, and then we're not going to do the noble gases. If you had helium, it would have 2 dots, but we're not going to worry about that. But if it says draw the Lewis dot structure of helium, it will have 2 dots. And then the remaining ones, say we had argon, if we have neon, everything else is going to have 8 dots. So all your noble gases have 8 dots except for helium, because the electron configuration of helium is 1s2. There's only 2 electrons total. All right, and so if I put my Na here, it has a dot. All right, so everything in this column, 1 dot. Everything in this column, 1 dot. Then we skip the D's. We're not going to do the D's. Then we go to the boron aluminum column. Everything has 3 dots. Then the carbon column, 4 dots. Nitrogen column, 5 dots. Oxygen column, 6 dots. The halogens, the fluorine starts it, 7 dots. All right. Again, dots are placed 1 to a side until all 4 sides are occupied. I don't care how you're putting on the dots. That's not important to me. As long as they have the correct number of dots, that's what is important. All right, so again, everything in column 1 is going to have an S1 ending. That means 1 dot. Everything in column 2 is going to have an S2 ending. That means 2 dots. Everything in the 3A, which is your boron and aluminum, is going to have an S2 and a P1. That's your 3 dots. Everything in the column with carbon is going to have an S2 and a P2. That's 4 dots. And then an S2 and a P3, 5 dots. S2, P4, 6 dots. S2, P5, 7 dots. All right, and then S2P6, they're all going to be 8 dots again, except for helium, which only has a 1 S2, and that would be 2 dots. All right, so the only one that's not every single member the same, and that is your halogens, or your noble gases here. Your noble gases, helium has 2, the rest have 8. Everything else, the column is consistent. 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 6 dots, 7 dots. Everything in that column will have that many dots. All right, so if we have calcium oxide, so calcium is in the +2 column. Oxygen is in the -2 column. What does that mean? That means when we take our calcium, and it has 2 dots because it's in group 2, it's going to react with oxygen, all right, and that is in group 6, that has 6 electrons. All right, so what's going to happen is this electron is going to pair up with this one, and this electron is going to pair up with this one, and you're going to end up with calcium that has no electrons, which is a +2, and an oxygen that has taken the 2 electrons from the calcium, and it is a -2. All right, so this is a transfer of electrons. The reason that you know that is because you know that calcium is a metal and oxygen is a nonmetal. And then you know it's going to be ionic. Then you know it's going to transfer the electrons, and you're going to get a plus and a minus, a calcium cation and an oxygen anion. All right. So the energy to remove an electron that we just did, that's your ionization energy. The energy to add an electron, that is your electron affinity. All right, so that's what we're doing with the calcium. We are making calcium going to a calcium +1 electron, and then we're taking a calcium +1 and going to calcium +2 and another electron. All right, and so that is our ionization energies that are happening. We are removing 2 electrons and making a calcium +2. With the oxygen, we had oxygen, and we're gaining 1 electron to make it O-, and then our O- is going to gain an electron, and then we get an O-2. And so we're doing an ionization energy, and we're doing an electron affinity. When you add all of these up, if you add them all up, all 4 of these reactions, the electrons cancel. All right, the O- cancels. Your calcium +1s cancel, and you end up with the same reaction we had before. The calcium, the element neutral calcium, reacts with the oxygen. We should whatever, and then you get a calcium +2 and an O-2. If you're balancing the reaction, though, it is a calcium plus O2 goes to CaO. There's 2 of those. There's 2 of those. When you're doing electron affinities, it is with an atom, so this is at not normal conditions, because oxygen is in normal conditions diatomic. All right, combinations of ionization energies, electron affinities is still endothermic. That means that the process requires energy. Okay, so you are requiring energy. So if we take magnesium, for example, in our lab, and we add oxygen, all right, we don't just sit there and look at it and it doesn't turn into MgO. All right, we had to heat it. We put it in a crucible and we had to heat it very hot. All right, so it required an activation energy. All right, now once you have the reaction going, then it is going to release energy. All right, so however, when the 2 ions bond, more than enough energy is released. All right, so it takes energy to get this going. All right, so we have to get the activation energy, but once it starts, then it's giving off lots of energy. All right, lattice energy is the change in energy that occurs when ionic solid is separated into the gas phase ions. All right, so when we look at our sodium chloride, all right, so we have step one. We're going to take our 1 mole of sodium and our 1 mole of the atom chlorine. All right, and it's going to require 147 kilojoules in order to ionize the sodium, the ionization energy for the sodium to make it sodium plus, and to electron affinity, the Cl. All right, so that is an endothermic process. All right, and then step two, then once you have your Na plus and your Cl minus, now they are attracted to one another. All right, and so then you have the NaCl compound, you have the ionic bond, which releases exothermic 493 kilojoules. All right, and then if you then make that a solid, okay, so you're in the gas phase here, and then then it forms a solid sodium chloride. It releases again a 293 kilojoules is released. Again, that is an exothermic. All right, and so when these two things make their ionic bond and form the Na solid, the total for step two is it is a 786 kilojoules of exothermic reaction. All right, and so that is the lattice energy. And so the overall, in order to get it started with step one, it was an endothermic reaction. Then it is very exothermic after that. And so the net is exothermic by a delta H of negative 639 kilojoules. Not going to do that one. All right. Give the electron configuration and the Lewis symbol for the chloride ion. All right, we've already done this. The electron configuration, this is Cl minus, and so that is your neon, and then a 3s2, and then a 3p. It would be 5, but it has an extra electron, so that is then a 3p6. That is the same electron configuration as argon. All right, so chlorine is element number 17. So that is always going to be 17 protons. If you're Cl, you're 17 protons, that never changes. What can change is the number of electrons. So here we have an extra electron. So if we have 17 pluses, we need 18 minuses in order to get a negative overall charge. 17 minus 18 is a negative 1 Cl minus. And so there is your electron configuration. The Lewis symbol is simply the dots, the number of dots. So for Cl, the number of dots is 7. For Cl minus, the number of dots is 8. And so you put 8 dots around your Cl, and that is a negative charge. And so your electron configuration is that of argon. So that's a neon, 3s2, 3p6, and then you have your 8 dots with the negative charge for your Lewis symbol. You can write out the entire electron configuration. I will always use the noble gas core. All right. Okay, 3A, 5A. All right, polyatomic ions. Remember, we had our memorized chart of polyatomic ions. Your PO4 minus 3, that's your phosphate. You've got your SO4 minus 2, your sulfate, your NO3 minus, your nitrate, your CO3 minus 2, your carbonate, your MnO3 minus, that's your manganate. Then you also had an NH4 4 plus, which is a polyatomic ion, that is ammonium. All right, and so these are your polyatomic ions. There might be more that I had you. Oh yeah, there's the chlorate, ClO3 minus, chlorate, bromate, BrO3 minus, your iodate, that's the IO3 minus. All right, so these are a group of atoms held together by covalent bonds as a group. They have gained or lost one or more electrons. They have a overall charge. So that is more than one atom with a charge. Polyatomic, more than one atom, ion, charge. All right, so most of them that we memorized were anions, negative charge, but there was the ammonium that had the plus charge. You have several oxidation states for your transition metals. Many of them will have a +2 ion. The only ones that do not, one is silver, does not form a +2 ion. I think there's a couple others, but most, not all, form a stable +2 ion because they easily lose the 2s electrons. All right, so when you're doing the electron configuration of manganese, you have Mn. All right, and then the noble gas core is argon, which takes up 18. Then you have the 4s2, and after the 4s2, you have the 3d. And so when our manganese has an atomic number of 25, and we want first the neutral Mn, we need to have 25. So we have the 5 for the 3d. All right, so remember, when you are removing electrons to make it a +2, you do not remove them the same way you put them in. You remove them out of the highest N energy level. So that is the neutral Mn. Your Mn +2 is your argon, and then simply a 3d5. All right, the 2 electrons removed are the ones from the highest N quantum number. And again, they're going to write out the whole thing, which is fine. All right, I will write that right here as argon. All right, again, how they write the answer. So the answer for the neutral is not going to be given this way. The answer is going to be written in number order. The 3d5 written first, the 4s2 written second, for the reason that when you remove them from the highest to the lowest. And so they will always put it in number order so that when you take electrons out, you take them out of the 4s. I don't care what order you put them in, but you must take the electrons out of the 4s2 for this problem because that is the higher N quantum number. All right, so the following are electron configurations for some ions. Which ones would you expect to see in a chemical compound state? Concept or rule you use to decide against or for any ion. All right, iron +2. One, we would say, yes, we would expect that because iron +2 is a stable, one of the 2 stable ionizations of iron is +2 and +3. However, they don't give the correct electron configuration of iron +2. Iron +2, you must take the electrons out of the 4s2 because that is a higher N quantum number than the 3d. Here, if you look at neutral iron, it is 3d6 4s2. All right, so the correct electron configuration of iron +2 is you get rid of the 4s2 and you are left with a 3d6. All right, and so iron +2 is stable, but the electron configuration of iron +2 is a 3d6. N-2 is not going to be stable. N-3 will be stable. All right, so N-3, that's the one that's going to give you the electron configuration of a noble gas. This is the correct electron configuration of N-2, but it is not going to be stable until you get a full P. So N-3 being a helium 2s2 2p6, that would be a stable ion. All right, so the zinc plus 2. So they did that one correctly. They took out the 4s2. So neutral had a 4s2 here. You take out the 4s2, you got a zinc plus 2. That is very stable. That is memorized when we had our first test, that zinc comes as a stable zinc plus 2 ion. And so that is the first one here. That is very good. Na plus 2, no, you will only see sodium as plus 1. All right, so you're not going to take, what they did was they had neon and they took an electron out of neon. Neon was the Na plus. Remember, the high jump in energy is when you take the electron out of the noble gas core. For Na plus 2, they took an electron out of the noble gas core. I'm not sure what this thing is here, but I think that's supposed to say 2. Again, that is going to be an unstable ion. You will not take an electron out of the noble gas core. Na is always plus, never plus 2. Calcium plus 2, that one is very stable. All right. So when you do a calcium plus 2, you're going to have argon, which is what they have here. All right. So this is the electron configuration of argon. So E and C are very stable and correctly written electron configurations. Na plus 2 is unstable. N minus 2, this is extremely unstable. Na plus 2. N minus 2, it's not stable. It's not wrong as written, but it's not stable. Fe plus 2 is stable, but it's wrong as written. That is not the correct electron configuration for Fe plus 2. All right, so Fe plus 2, again, that would be stable if they took the electrons out of the correct subshell. Nitrogen wants to be minus 3, not minus 2. All right, so this one is great. Na plus 2, definitely not. You're only going to have an Na plus, and then your calcium plus 2. That one, again, is a perfect electron configuration for the calcium plus 2. All right, so we talked about atomic radius, and we talked a little bit about ionic radius, and here it is again. So an ionic radius, that means it's going to have a charge. Remember, more negative is larger. Or you could say, instead of more negative, less positive is larger. All right, so when you have a radius, again, you're looking at the protons that are holding on to the electrons. All right, so if you have extra electrons, they're going to be floating way out here, and that's going to have a very large radius. If you have extra protons, it's going to suck the electrons in. Remember, protons have a plus charge, and electrons have a minus charge. All right, so if you have a bunch of plus charges holding a few minus charges, they're going to hold it very closely. If you have a lot of negative charges, more than your positive charges, well, then those are going to be way far away and have a large radius. All right, so again, you have your Na, you have your Na plus. All right, so what does that mean? Well, Na plus, here you have Na, which is 11. Here you have Na, which is 11. If you have 11, you have Na. If you have Na, you have 11. 11 protons is sodium. That never changes. Again, what changes is the number of electrons. So this has 11 electrons, and it is neutral. All right, and so that is your atomic radius. So this is an atom. All atoms are neutral. So this is an atomic radius. All right, so here we still have our 11 protons. So our 11 protons are in the center. And then now we only have 10 electrons surrounding it. And so 11 protons can easily hold 10 electrons, and it holds them very tightly. And so this is a small ionic radius. So this has a charge. If you have a charge, then you're called an ion. So this is an ionic radius. All right, so same thing here. Chlorine is 17. If you're 17, you're chlorine. If you're 17, you're chlorine. 17 protons every single time. Here is 17 protons, and here is 17 electrons. Again, this is neutral. This is your atomic radius. All right, so now you have an extra electron, 18 electrons. So you still have 17 protons in the center, but now you have not just 17, but 18, you have that one extra electron that is going to be far away from your nucleus. And so your atomic radius is measuring from the center to the outermost electron. And so this is an ionic radius. All right, so when you become positive, that means that you have more protons. Protons are in the nucleus, and you're going to have less electrons, and these are going to be small. All right, and when you become negative, that means you have an extra electron. Same number of protons, but an extra electron. That extra electron is far away, and you will have a large radius. All right, when you see iso means the same. Isotonic solutions, all right, that is the correct concentration of solution. Isoelectronic, all right, so this is same. Electron is in the word, same electron. All right, so it's the same number of electrons. So when you see isoelectronic, it's just asking you, do you have the same number of electrons or not? All right, so neon on the periodic table is number 10. Sodium is number 11. Fluorine is number 9. So as neutral, they are not isoelectronic, because neutral, that would have 10 electrons, 11 electrons, and 9 electrons. But as ions, all right, so this has 10 protons, 10 electrons, because neon is neutral here. Sodium, we just did it, that is 11 protons, but now it has a overall plus charge, so still only 10 electrons, same as neon. So they are called isoelectronic. They both have 10 electrons. Here you have 9 protons, but we have an overall minus charge, which means we have one more electron than proton. Again, that means 10 electrons. And so when you write 10 electrons for all of these, then they are called isoelectronic, which means same number of electrons. All right, so all isoelectronic means is same number of electrons. All right, and so again, the more negative is the larger. All right, so and then the more positive is the smaller. So increasing size, you got your Na plus, which is the smallest radius. All right, so the more positive is going to be the smallest, and then you got your neutral neon. And then negatives are the largest, all right, largest radius. All right, so more negative is the larger radius. If they have the same charge, then we use the same rule as we did for your atomic radius. Remember, atomic radius, smallest is up here. All right, so if you want to go to smallest, it decreases this way, it decreases this way. If you like increase, point the arrow the other way and it increases. All right, increasing ionic radius. So this one, you don't have to do anything except say this is the most negative, this is the most positive. So SR plus 2 is the smallest, followed by your BR, which is only -1, followed by your SE, which is a -2. The more negative, the larger. The more positive, the smaller. And so you don't have to do anything except know that charge. This means you have 2 extra protons holding on the electron. So that's going to be very tight. Here you have 1 extra electron out there. Here you have 2 extra electrons out there. And so it's going to be even larger. All right, so that was ionic bonds, making cations and anions. Covalent bonds, this is when we're going to share electrons. So we're going to share electrons. And this is when we have 2 nonmetals. All right. All right, so when we do hydrogen, we have our dot structures. And so we have H in column 1, which has a dot. We have another H in column 1 that has a dot. And so we then share. H is a nonmetal, H is a nonmetal, and it shares. and you have H. This shows a bond. All right, and so that is the same as showing this. This is the same. So you can draw it this way, which I will do every single time, or you can draw it this way. It doesn't matter. All right, I always put in a bond. I know that a bond is 2 electrons. If you want to draw the 2 electrons this way, that's fine as well. I will always have a line, and a shared line is a covalent bond. So this is showing a covalent bond. And every bond is 2 electrons. So all bonds require 2 electrons. So when I show this as a bond, it is 2 electrons, or you can show the 2 dots between the 2 atoms. If you show it this way, this is a little strange, but fine. You will not see it written this way. You will see it both of these ways, though. All right, and so they are sharing the electrons. All right, if we want to take an H plus and add NH3, all right, so what happens here is a different kind of bond. This is called a coordinate covalent bond. And what that means is both electrons come from the same atom. All right, so that's what the difference is. Both electrons are donated by one atom. So when we did the hydrogen, it was 1 electron from this H and 1 electron from that H, and then you share and you have your bond. All right, so this is the usual covalent bond, 1 electron from each atom to make the bond. In a coordinate covalent bond, both electrons are from the same atom. And so we're taking both of these electrons and no electron on H plus and making a bond. And so this is the Lewis dot structure for NH4 plus, which is one of our polyatomic ions. All right, once you form that bond, it is exactly the same as all 3 of these other bonds. So it is the same as an NH bond. So you can't say, oh, this is the one that we made. These are all the same. So once that is formed, they are indistinguishable. All right, all the NH bonds are identical at that point. So when we talk about a coordinate covalent bond, it's about how it is formed. It is formed by taking 2 electrons from the same atom and forming a bond. Once it has been formed, it's the same as any other covalent bond. All right, octet rule. All right, so we have some, whatever. Hydrogen has the duet rule. All right, so you have a duet rule if you are hydrogen. That means it always has 2 electrons, and I call that the duet rule. All right, so this is row 1. Row 1 has hydrogen and helium. Helium does not do reactions, and so we only have to worry about hydrogen in row 1 having a duet rule. If you ever have more than 2 electrons on a hydrogen, you have the wrong answer. Hydrogen, 1 bond, which is 2 electrons, and that's it. Never more than 1 bond. When you're looking at row 2, then you have the octet rule. That means you have a maximum of 8 electrons. And why is that? Well, in row 1, all we have is the 1s2. That means 2 electrons is the maximum, duet rule. In row 2, we have the 2s2 and the 2p6. That is 8. And that is the octet rule. We cannot have more than 8 electrons when we are in row 2. Once we are in row 3, and energy level 3, then we have the 3s2, the 3p6, and we also have the 3d10. And so row 3 can have up to 18 electrons. Up to 18 electrons. However, 8 electrons is the most stable. Now you can call that the octet rule because 8 electrons is the most stable. But you can put in up to 18 electrons and not violate any rules. That's row 3. In row 2, if you put in more than 8, you have violated the octet rule, and that does not exist. All right, when we do bonds, we can have a single bond, which we showed, hydrogen, hydrogen, that has a single bond. When we do a double bond, an example here would be oxygen. So we know that hydrogen is H2, and that is the Lewis structure for hydrogen, H2 diatomic. We also know that oxygen is diatomic. That means that an O is going to react with another O, and it's going to form O2. Now, what happens here is that this shares and this one shares. And so when you have oxygen, it has a double bond. And note that you have then lone pairs. If you either have bonding electrons shown in a bond, or you have non-bonding electrons shown as a lone pair, as just 2 dots. They are not bonding electrons. They are non-bonding electrons. And we also know that nitrogen, all right, nitrogen has 5 electrons. And again, I said I didn't care how you write the 5 as long as it has 5. Because when I'm writing nitrogen this time, I'm going to write it this way for a reason. We know that nitrogen is also diatomic. What happens is we share electrons here for one bond. We share electrons here for a second bond. And we share electrons here for a third bond. And so nitrogen has a triple bond between the 2 nitrogens. All right, and so we see that a single bond, we showed it before, that was H with a dot plus H with a dot, and then that made the bond. And so a bond is 2 electrons. So if you have a single bond, it is 2 electrons. All right, here a double bond, we needed 2 electrons for the first bond and 2 electrons for the second bond. So a double bond has 4 electrons. And then a triple bond, 2 electrons for that bond, 2 electrons for that bond, 2 electrons for that bond. This one is 6 electrons to make a triple bond. All right, so when we do double bonds and triple bonds, again, we're going to do carbon, nitrogen, oxygen. So this is organic chemistry, a lot of double bonds in organic chemistry. All right, anytime you have carbon, you're going to have organic chemistry. And so CN, so that was one of our ions, CN minus. That is also a triple bond. So that has a carbon triple bonded to nitrogen. And each one of these has an electron pair on it. And then very soon, we're going to be talking about how to put the charge on the different atoms. All right, so when we look at CN minus, all right, the nitrogen had 5. So sometimes, a lot of times, it's best. I said they don't normally write it this way, but it is very handy to write it this way when you talk about the charge of the atom. All right, so when we have our dots there, we see that nitrogen came in with 5 dots. And we look at the periodic table. Yes, nitrogen should come in with 5 dots. Then we look at the carbon. It came in with 5 dots. We look at the periodic table and say, no, carbon should only have 4 electrons, not 5. It has an extra electron. And that's why the carbon has the negative charge on it. When you do CN minus, it is the carbon that has the negative charge. All right, so ionic bonds are, of course, very polar. They're ionic, as polar as you can get, plus and minus. Now, covalent bonds, we're going to have polar covalent bonds, and we're also going to have nonpolar covalent bonds. All right, and so we're going to need electronegativities for our different atoms to determine if we have a nonpolar covalent bond or a polar covalent bond. And so it is the difference in electronegativities. All right, so your electronegativity is the measure of the atom's ability to hold on to electrons. All right, and it is related to electron affinity. So the highest electronegativity is fluorine with a perfect 4.0. All right, so it increases to fluorine. It will increase to fluorine. We're talking about electronegativity. They will increase as you go towards fluorine. So from left to right, it increases, and from bottom to top, it increases, right? So fluorine wants to hold on to its electrons the tightest, all right? And so when we're talking about a polar covalent bond, when you have a bond, let's say you have an H with an F bond, all right? The electrons here, since we now know that fluorine has the strongest electronegativity, that means that the fluorine is pulling the electrons to it. All right, so the electrons are closer to the fluorine. So if we drew the bonds as dots, you would have your H and you would have your F, and your two electrons for that bond are going to be much closer to the fluorine than they are to the hydrogen. It is still sharing the electrons, but they are very closely held by the fluorine, not near as close to the hydrogen. And so your fluorine has more electron character there, and so it has a partial minus, not a full minus, a partial minus. When you draw, I should fill in all of the electrons here. When you draw the F with this bond here, all right, so it is partial minus, and the H then is partial plus. All right, so when you have two atoms that have a different electronegativity, the one that has the higher electronegativity, that means that the electrons are going to be closer to it, and that's going to give you a partial minus. That delta means partial. It is not a full minus. This is not like NaF, which would look the same, except this is ionic because that's a metal and that's a non-metal, and that would be a plus and a minus, not a partial. This delta means partial, not a full minus, partial minus. It is still sharing. It's not equal sharing. The electrons are closer to the fluorine. NaF, this isn't sharing at all. The fluorine took, the electron got transferred to the fluorine. All right, it is not sharing at all. When you have a unequal sharing of electrons, then you have your partial plus and minus, and you know that because you have two nonmetals versus a metal and a nonmetal. All right, so here are the electronegativities, and so you will see that my trend that I told you, if you go this way, you're going to increase, and you do across any given row, you're going to increase from left to right. All right, and then from any given column, when you go up, you're going to increase. So look at any column, go up, and it's going to increase. The numbers that you will have to know for the test. You have to know the trends for all of them, but the actual numbers you will need to know. The 2.1 for hydrogen. And what's nice about lithium through fluorine is they have the perfect 4.0 for fluorine and the 1.0 for lithium. And it increases by 0.5. You got the 1.0, the 1.5, the 2.0, the 2.5, the 3.0, and the 3.5. So you need to know that whole row. It's easy to remember because it simply increases by 0.5, starts at 1, goes to 4. You also need to know your halogens, which is chlorine is a 3.0, bromine is a 2.8, iodine is a 2.5. All right, and then of course in the hydrogen, and then we're going to go with sulfur at 2.5 and phosphorus at 2.1. Those are the ones that you have to know. Any other electronegativity that you need to know is going to be based on your periodic trends. And we are going with the periodic trends. We're not going with any of the exceptions. There are plenty of them. We are not going to use any exceptions. All right, so it increases as you go to the right. You can look and see that some do not. Increase as you go up. And of course, some of those also are not true as well. But that is our general trend that we're going to go with. All right, so if your difference is very small, then you're going to be nonpolar. If your distance is very large, well, it depends on how large, very, very large, you're ionic. That's a metal and a nonmetal. And if your distance is large, not very large, then you are polar. And if it's small, then you're nonpolar. So the difference between ionic and polar and nonpolar. I think the difference here is like 1.6. When you are a difference of 1.6 or greater, then you are an ionic bond. Nonpolar is less than or equal to 0.4. And so your polar is between 1.6 and 0.4, right, but more than 0.4. So say 0.5. All right, so to be nonpolar, it has to be less than or equal to a 0.4 difference. So if we go back and we look at a CH bond, all right, so CH, extremely common in organic chemistry. All right, so you got carbon, which is a 2.5, and you got hydrogen, which is a 2.1. And so the difference, you simply subtract it. Difference means subtraction. So you subtract those two numbers. So the difference is 0.4. So we now know that if you are 0.4 or less difference, then you are nonpolar. And so a CH bond is going to be a nonpolar bond. All right, so because the difference is 0.4 or less. If we look at an OH, another very, very common organic bond here, very common. You got oxygen, which is 3.5. And you got hydrogen, which is 2.1. The difference, again, subtract 1.4. So 1.4 is the difference. This is your polar covalent bond. All right, and we knew it was going to be a covalent bond because oxygen's a nonmetal, hydrogen's a nonmetal. We knew this was going to be a covalent bond because carbon is a nonmetal, hydrogen's a nonmetal. All right, so to determine whether it is a nonpolar covalent bond or a polar covalent bond, you need to know the electronegativities, take the difference of those two, and if the difference is less than or equal to 0.4, it's nonpolar. If it is greater than 0.4, it's going to be polar. All right, and so again, so nonpolar, we're not going to put partial minus, partial plus. If you did, I wouldn't count that wrong. If you don't call it nonpolar, it is wrong. So nonpolar bond, all right, it is not perfectly equal. It has a 0.4 difference. All right, but when you have your OH, then you must put where the minus and the plus is. Again, the number is how strong that atom holds its electrons. All right, oxygen is the second strongest. The only one stronger than oxygen is fluorine. So every time you have oxygen, it's going to be delta minus unless it's connected to fluorine. Every time you have fluorine, it's delta minus. Nothing has a higher electronegativity than fluorine. So your oxygen has the delta minus, and then your hydrogen has the delta plus. So the one with the higher electronegativity, the electrons are closer to it, it is partial minus when you have two nonmetals bonding. The one, of course, that has the smaller number will be delta positive. The electrons are not being held. It's being pulled away by the higher electronegativity. All right, so when you're nonpolar, if you don't put plus and minus, that's fine. If you do it correctly, the higher number, carbon, is going to be a delta minus. The hydrogen would be a delta plus. All right, but that would be a very, very, very small delta minus and delta plus, so small that we call that a nonpolar bond. All right, so the numbers you're looking at are 0.4. All right, that's really, if you are two nonmetals and you are less than or equal to 0.4, then you are nonpolar. If you are greater than 0.4, you are going to be polar. Ionic, that is hydrogen sometimes, again, thinks it's a metal. So if we did the HF and got a 4.1 or 4.0 and a 2.1, note the difference here is a 1.9. And that's why I don't put this one up here. So this one would be ionic, although I prefer this one to be called, since it's a nonmetal and a nonmetal, and that's really Yeah, not the reason, but I would call this one a polar covalent. So I'm not really hooked on the 1.6 number. I am very hooked on the 0.4 number. All right. So I would probably accept either answer. What's the difference? 1.6 if you say it's greater than, or 1.9 if you say it's greater than 1.6, so it's ionic, full credit. If you say I got two non-metals, so I'm going with polar covalent, great, full credit. And of course, yeah, that has some ionic character. You have a very strong delta minus for your F and a very strong delta plus. I would not put it as a full plus and minus, but the numbers say yes, so I would not count that wrong. All right, so again, carbon. So you've got your 2.0, you've got your 3.0, 2.5, sorry, 2.5, 3.0. Sodium, I think it's 0.9, 4.0. You got your, we already did this one, 3.5, 2.1. All right, so again, you're looking at the difference. When you do a carbon and a nitrogen, that's only a difference of 0.5, but 0.5 is greater than 0.4. All right, and so this has your delta minus, and this has your delta plus. Again, whatever number is higher gets the delta minus. Whatever number is lower gets the delta plus. Sodium is below lithium, which is 1, so it's less than 1, so I went with 0.9, doesn't matter. Anything less than 1 would be a fine number here. All right, so the difference here we know is 3.1. What we do know for a fact is that it's at least 3, because lithium is memorized as 1.0. And so it decreases as it goes down. So this Na has to be less than 1. All right. And so this then number is going to be greater than 3.0. All right. Doesn't matter. It only has to be greater than 1.6 to make it ionic. Although, since it's a metal and a non-metal, we're going to call it ionic anyway. All right. And then again, this one was the 1.4. All right, so this one also is a polar covalent. All right, so they would say increasing polarity. All right, so the least polar is the CN. It only has a difference of 0.5. All right, followed by your OH bond, which has a 1.4 difference. Followed by your NAF, which is ionic, and NAF, which is ionic and has a difference of 3.1. So you got your 0.5 difference, you got your 1.4 difference, and your 3.1. All right, so your delta minus here on the oxygen, delta plus on the hydrogen. All right, so note when you have your NAF, that is a full minus and a full plus. That is an ionic bond. The other ones that are two nonmetals, the delta minus goes on the higher number, the delta plus goes on the smaller number. All right, doesn't matter what order you put them in. You can write it C N, you can write it N C, it doesn't matter. All right, but the negative delta minus always goes on the higher electronegativity. The delta minus goes on the higher. If you are ionic, well, then you get a full plus and minus. This delta means partial. So that is a partial minus and a partial plus, not a full plus and minus. All right, writing Lewis electron dot formulas. All right, so we're going to calculate the number of valence electrons, write out a skeletal structure, distribute electrons to the atoms surrounding the central to give the octets. Again, unless you are hydrogen, remember hydrogen has a duet rule. All right, so let's do the OF2. We're going to do it both ways. All right, so oxygen's in column 6. So we write 6 dots around the oxygen. Again, I don't care which way you write 6 dots on an O. Fluorine has 7 dots. All right, so I don't really care how you write the 7 dots. I will always write my 7 dots this way. Since I have a non-metals, all of these are non-metals, I am looking at covalent bonds, which are going to share electrons. All right, and so the 1 electron that is on the fluorine is going to share with the 1 electron that's on the oxygen here. The 1 electron that's on the fluorine here is going to share with this 1 electron. All right, so note, electrons want to be paired up. We don't want any unpaired electrons. And so when you are finished, you have the Fs that have the paired electrons all around it, and then it's going to share electrons with the O. All right, and that O has electrons, and then I drew it down here. And so then you have your F here, and then you have your electrons around it. So there is the Lewis dot structure of OF2. All right, the other way to do it is just to give the number of valence electrons. The number of valence electrons are the dots around your atom. And so this would be 6 for your oxygen, 6 dots. And this would be 7 and another 7. So each fluorine has 7. And so you would add all of those up, and you would get your 20 valence electrons. All right, and so your first atom is the central atom. So the first atom is central, unless hydrogen. Hydrogen can never be a central atom because hydrogen can only have 1 bond, because 1 bond is 2 electrons. Hydrogen has the duet rule. All right, so the first atom is the central atom. So I write my O, it's the central atom. And then I have an F coming off of one side and an F coming off of the other side. All right, and now, now I put in 2 bonds. And so I had my 20 valence electrons minus 4. This is the 2 bonds. And so I have 16 electrons left. After I put in these 2 bonds, that's the 4 electrons that I have to subtract. And now I have to see if that is enough electrons to give all of my atoms an octet. All right, so this is 2 shared between the F and the O. This is 2 shared between the F and the O. All right, so this F has 2 here, and it needs 6 more. This F has 2 here, it needs 6 more. And so there is your octet for the fluorine. This O has 2 here, this O has 2 here. To get 8, we need 2 up here, 2 down here. And so when we add them up, 2, 4, 6, 8, 10, 12, 14, 16, that is the perfect number to give all of them an octet. All right? And so you can write the Lewis structure that way, or you can write the Lewis structure this way. You could also put it as dots if you want, instead of bonds. I do not, again, do the dots. I will show you that that is exactly the same. I never put in the dots here. I always put in the bond. But you need to know that a bond means that you have 2 dots, 2 electrons shared between those 2 atoms. All right, and when we do NF3, all right, so N is going to have 5 electrons. If you look on the periodic table, it is in period 5. All right, I have 3 Fs. Each F is going to have 7. And note how I'm going to line these up. 7. I can write the 7 any way I want. And so note that I'm lining this one up, so that is right next to that single electron, unpaired electron. And then I'm going to write the 7 on this one lined up to be right by that single electron. And then I'll write the other one over here lined up by this single electron. All right, and so you can, well, that's an actual correct answer right there. I will always write it with an electron pair here, then an F, then an F, and then an F. I always show mine with bonds, and then you put your electrons around, and you show that each F has an octet and the N has an octet. When we look at the octet, octet counts shared. So we have 8 here, we have 8 here, we have 8 here. And when we look at nitrogen, remember, shareds count. We have 8 here. And so all of the atoms, the 1N and the 3Fs, they all have an octet. All right, if we are doing the counting electron rule, again, nitrogen is in column 5, so you add 5 plus 7 plus 7 plus 7, or simply 7 times 3, you get 26. For your 7 times 3 plus 5, you have 26 valence electrons. The first atom is your central atom. You write the N. Then you bond it to 3 Fs, an F, an F, and an F. Again, you put in 3 bonds. You have to know that each bond required 2 electrons. So you have your 26 valence electrons minus 6 electrons for the 3 bonds. And you have 20 electrons left. And you have to see if that's enough electrons to give all of the atoms an octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That is the perfect number of electrons to give all of the atoms an octet. And so it doesn't matter how you get the Lewis structure. You can do it by counting the electrons and putting in bonds, subtracting electrons, and doing it that way. Or you can write the dot structures of each of the atoms and then combine them to get the structure that way. All right, this is very important, Lewis dot structures. Many points on the test will be doing this. So make sure you're very comfortable doing this kind of chemistry.